Awesome. Okay. Well, thank you guys all for coming. This is the USACO Silver February 2022 problem review. I am the Director of USACO Education at Breakout Mentors. We are a tutoring service, specifically, at least my sector is centered around USACO education, helping you guys promote up the ranks as fast as possible by pairing you guys with mentors who have already reached the gold and platinum divisions. So if any of you guys aren't already students, would highly recommend checking us out. All the mentors really know their stuff and they're wonderful at what they do. So yeah. We also have other sectors though. So for students who are interested in learning like machine learning, iOS, Unity, so on and so forth, we also have sectors for that as well. But what I do focuses mainly on competitive programming and pairing you guys with mentors for that. So yeah, with that said, let's do what you guys came here for. Let's dive into the problems. I'll say what I said at the beginning of the bronze chat, or at the beginning of the bronze session, which is that if you guys have any questions, just stop me. I think my goal is just to make sure that you guys understand what's going on here. And obviously that's not going to happen if I start plowing ahead of where you guys were at in the contest. So please feel free to like raise your hand or turn off your mic or anything like that at any point. I'm happy to answer any questions. Yeah, I will share my screen. I'll start with redistributing gifts. Can you guys see? Thumbs up. Okay. All right, so redistributing gifts. I think this might have been the toughest problem or one of the tougher problems, honestly. I think the other ones were mainly the implementation. But anyway, we have a set of gifts that Farmer John has distributed. And he kind of just gave every cow the gift that they match their number, doesn't necessarily match up with their own preferences, right? So we want to know, given the lists of each cow's preferences, how do we swap such that each cow kind of gets what they want, right? And this problem is worded a little bit confusingly, where each cow, we're actually going to potentially do a different assignment to get it the gift it wants, right? So for the first cow, who wants 1, then 2, then 3, then 4, it's just going to stick with the gift it receives, right? The second cow, it wants 1, then 3, then 2, then 4, right? And it can swap its gift, the second gift, with the third cow, who wants the second gift more. So these cows can kind of exchange the gifts they have, and they can both get what they want in this case, right? The last cow doesn't really have any power with its gift. No one really wants the fourth gift, unfortunately. I don't know what it is, but no one wants it, so they end up keeping that gift, unfortunately. So the question is, how do we figure out what gifts each cow can get? And it's not so intuitive, but the biggest observation is we can represent this as a sort of directed graph, where if cow I can exchange, we'll say CE, with cow J, that means cow J wants cow I's gift. We'll draw an arrow from node I to node J. So can someone help me out and tell me maybe what some of the edges are with this model for this particular sample case? So which cows are connected to which cows? Who can exchange gifts with who? Let's see, 2 to 3, awesome. Cow 2 can give their gift to cow 3 because cow 3 wants that gift, right? Can cow 3 give their gift to cow 2? Yes, so this is actually bidirectional here. What other connections do we have? It's a bit of a tough question, right? Because it seems like there might not be anymore because no one is going to give their gift and like it anymore. Cow 4 actually cannot give their gift to anyone else. And the reason for that is a little subtle. It's in the direction of the definition we came up with. Well, it's a very good question to ask. We said we only want cow I to be connected to cow J. Yes, yeah, that's the idea, right? So we only want cow I to be connected to cow J if cow J wants cow I's gift. So if we're giving them a gift that they will accept and want to give up, given what they have, right? So in this case, cow 1 can give their gift to anybody else as well, because everyone wants cow 1's gift, but no one wants cow 4's gift, right? So we have these edges here. Cow 1 can give their gift to anybody, and cow 2 and 3 can give their gifts to each other. Does this model kind of make sense? Is everyone feeling okay so far? Okay. Cool. Can I get some more thumbs ups in chat? I know Kang's following, he's doing great. How's everyone else feeling about this? Awesome, okay. Cool, thank you guys. Okay, so with this model, can someone tell me how we can find the best gift that, say, cow 3 can receive? I'll make that a different color. I'll make my pointer is a different color. So we want to know what's the best gift that cow 3 can get. What can we do to figure this out? Now that we have this graph set up, how do we use it? Any ideas? Yeah. So the idea is we can DFS out. And in the graph, it just means like doing some kind of flood fill, right? We just try to find all the nodes that cow 3 is connected to. Yes, exactly, right? That's awesome. You guys totally got it. And the reason this DFS kind of works, this flood fill works, is because when we have a path from one node to another node, that means there's a set of exchanges that cow can make that'll get it to another gift. And what that means is, say in this case, we know in this case actually that there's a path from cow 3 to cow 2. And that path has one edge in it. It's from 3 to 2. And this edge represents cow 3 exchanging their gift with cow 2. And we know that this is possible because we have an edge there, which means that cow 2 will accept cow 3's gift, right? Now, what does this look like when we have multiple edges? Say, for example, we have a graph that looks like this. So we have cow 2 connected to cow 3, connected to cow 4, connected to cow 5. And we say, oh, this means that we can get the 5th gift, right? And the reason for this is because we can take cow 3's gift, or cow 2 can take cow 3's gift by giving it the 2nd gift, right? So now cow 2 will have the gift 3. And since there's an edge from 3 to 4, that means cow 4 will accept the 3rd gift, right? So we can exchange the 3rd gift for the 4th gift. And now since there's an edge from the 4th cow to the 5th cow, that means cow 5 will accept the 4th gift. And so we can end up with the 5th gift as required. Does that kind of make sense? So if there's a path from any cow to any other cow, that means the source cow can end up with the destination cow's gift. Does that make sense? Any questions on that? Is everyone totally lost? I can backtrack too. Makes sense, makes sense. Is anyone confused? Everyone's good. Okay. But why? That's a good question. So what is the question? What's the reason for this graph, or why is this the case? Would you mind elaborating a little bit? Sorry. Should we calculate the origin cow should get this gift? Should we calculate the origin cow? Okay. So why do we want to know if there's this path from some source cow to some destination cow? That means that the source cow can get the destination cow's gift, right? Why does that even matter? Why do we care? And the idea is, well, if we now know which cows can get which cow's gifts, we can figure out the best gift that the source cow might hope to receive, right? So we can figure out now if 2 really wants maybe the 4th cow's gift, since there's a path there, we know it can get it, right? But if there's not a path, say that maybe this edge doesn't exist, we know there's no way for cow 2 to end up with cow 4's gift, right? So we can check the priorities that 2 has and kind of figure out the best gift it can get given the node that's connected to, right? And this goes back to what everyone else was talking about before with the flood fill idea, where we can actually check, given our center node, say 2 is the node we're trying to figure this out for, we can figure out all the different nodes it's connected to, right? And figure out, of the ones it's connected to, which of those gifts it wants the most, and that will be our answer for 2, right? So if it really wanted gift 4, and there's a path to gift 4, which there is here, then that'll be our output for 2, for the second cow. Does that make sense? I kind of chose these numbers arbitrarily, but you can do this for any of the cows, right? You can do this DFS for any cow. Kenny, is that okay? Yeah. So that's a really good question. I thought the problem was worded very confusingly in this sense. You actually can end up with 2 cows getting the same gift, quote unquote. And that's because for each individual cow, you want to figure out the best assignment individually, right? You want to say, like, what's the best case for this cow? And we don't care about all other cows. So we might actually end up with multiple different assignments, multiple different optimal assignments. And the cow that we're optimizing for is the ith cow for each assignment, if that makes any sense. So if we're looking at the first cow, we want to choose the reassignment that benefits the first cow the most. The second cow, we want to choose a potentially different reassignment that benefits the second cow the most. So we might end up with some overlap in which cows receive which gifts, because the cow we're optimizing for is different in each of these assignments. Does that make sense? Very good questions, by the way. Really appreciate this. The main idea is we can have multiple assignments. Yeah, it really is worded really, and I totally had the same problem with it. But yeah, very, very interesting idea for sure. Cool. So basically, we can do a DFS for every single cow. Is this fast enough? What do you guys think? It is. Why is it fast enough? Someone give me some run times. Yeah. Awesome. Does anyone have the runtime for this algorithm? If we do a DFS from every cow, construct a graph and then do a DFS. N squared. Close. Really, really close. It actually ends up being n log n. Interesting. Worst case n squared. So the reason I think it actually does end up being n cubed, although I'm honestly not 100% sure about that, so you can correct me if I'm totally wrong. But the idea is the number of edges we can have could be quadratic potentially, right? I'm not sure there's actually a permutation that exists here, but I think you could have it such that you expect there to be n squared, like cows that want other cows' gifts, right? And if remember the runtime of DFS or BFS or flood fill in general is n plus e. So if this is n squared, yeah, or I think it's like a cycle or something like that. That's a good point. But yeah, the idea is if we have n squared edges in this graph we've constructed, then running a DFS is going to take O of n squared time. And so if we do this n times, we end up with an O of n cubed algorithm. But yeah, like everyone said, this is totally okay. N is like 500. So regardless of what we do, we're kind of okay. I think 500 cubed might have been pushing it anyway. So you guys are probably right that it's around like n log n or n, I don't know. But yeah, the idea is we're totally fine here. We can just do this DFS. And so this is our solution, is to construct this graph and then do a DFS for every cow. Is everyone okay with that? Does everyone have any questions? Yeah, that's exactly right. And I'm not even sure. The change if you use BFS? Good question. The answer is no. The runtime is the same. It's more about just preferences there, I think. Some people like DFS over BFS just because it's faster to implement, and some people like BFS over DFS because you can get Stack Overflow with DFS sometimes, depending on how many times you're recursing. But yeah, the runtime of the two is the same for flood fill, at least. So it shouldn't matter here. Would n cubed work in Java in time? Very, very good question. You know, I'm not sure, and I think it. So this is probably, I'm probably just wrong about the number of edges in this case, but I think if it's a very low constant, then you're okay, right? So if the number of edges is like n squared over like 5, then you're probably okay, right? Because that ends up being like 125 mil divided by 5, and you end up with like 25 million, which is semi-okay. It's a lot for Java. It's reasonable for C++. It worked for around 80. Interesting. Yeah. Thank you, though. Good question. Okay. Any other questions before we move on? That was kind of quick. This question like basically just requires some rereading, and then the really big observation that we can turn this into a graph and run some DFS on it. So not too bad once you make that observation, but it's a big observation. Do we have any other questions, or are we good? Give me a thumbs up if you guys are ready to move on. Go to the next spot. Thumbs up, Jaden. Okay, awesome. Okay. Cool. Okay, so move on. Thank you guys. Okay. Cool. Next problem. Okay. Should we do this one? Oh, wait, am I in the right? Oh, we're in gold. Whoops. Not here yet. Okay, robot instructions. This problem was interesting. Thought it was kind of, what do you guys think? I would love to hear you guys' opinions on this because I didn't take this contest, obviously, but I'm always curious about what you guys think about these kinds of things and the problems and stuff. Do you guys think this was interesting? You guys think it was super grindy? Did anyone solve this problem? I think it might have been the hardest of the three, maybe. No response. I think that doesn't know. We got yes, yeah. The numbers are very big. This is true. Yeah. Okay. Yeah, I think this is my experience as well. Good set. Ooh, fun stuff. Yeah. So yeah, very interesting in that sense. I think depending on how you approach this problem, you either loved it or you hated it. So there's one approach to this problem where you used hashing, and that was really annoying, or at least it was annoying to me when I tried it with Java. But if you use a smarter, it was smart. Benchy had a really clever solution for this. They didn't necessarily need, but made this a little bit easier and was solvable in Java and stuff. So the idea is we have 40 instructions, right? We have 40 moves where we want the robot to go from point A to point B, or point G, I should say. And we have all these 40 instructions. It's 7 here, but it could be up to 40. To get the robot on a 2D plane to this position, right? We want to know how many different ways can we get there. So if n is 20, can you guys tell me a way to solve this? So if n is 20 instead of 40, How do we solve this? Think brute force. Think very, very brute force. Yes. Yeah. Awesome. Exactly. Exactly, right? So if we try all subsets of the 2 to the n instructions, where n is up to 20, the idea is we can figure out all the different possible locations we could end up at, right? So for example, if I chose, that's not a subset, that's a location. If I chose this and this and this, I would end up at 310, right? And I can figure out all the different possible ending locations I can end up at and count the number of ones that end up at 510, right? And that'll just be my solution. Now, the number of subsets, like people have pointed out, is just 2 to the 20 or 2 to the n, where I check for each instruction, whether I include it or exclude it in our subset. And so since I have 2 choices for all n subset, or for all n instructions, excuse me, the number of subsets is 2 to the 20 or 2 to the n. So this is doable if n is 20 or less than or equal to 20, right? But now n is 40, which makes this a little bit harder, right? So since n is 40, does anyone have any ideas on how we can change our approach to this a little bit? We can't brute force anymore, unfortunately. But what else can we do? DP, interesting. That's a cool idea. Anyone else? I feel like when you're in Silver nowadays, it's just like, there's gotta be some DP in here. Greedy loop, okay. The answer is no, Kang. Let people figure it out. We good. Okay, greedy loop. Nico, what do you mean by greedy loop? That's interesting.
Like choosing things that put you in the general direction of it.
Okay, okay. So some heuristics. That's cool. Interesting. The answer is actually a lot more straightforward than that, but that sounds really cool, and I'd love to try that out. I think you could definitely get some constant time benefits from doing something like that. But there's actually a much simpler solution that's still very brute forcey. The answer is we can actually do go back to 2 to the 20 like we had before. Does anyone kind of see how? Let's say we only considered half the problem, right? Say I only wanted to know all the spots I could reach with the first half of instructions. Can I still do that? Kang says yes, he's read the solution. Anyone else? Yes. Yes, exactly. Barrage has it. That's awesome. So the idea for this thing now is if we cut it in half and we only know, we do the same brute force we had before, but for the first half of instructions, we can figure out all the different locations we can get to just using the first half of instructions, right? So if I just, so if I just use the first 3 instructions here, I can try all 2 to 3 different subsets and figure out all the different locations I can reach. And then in the second half, I do the same exact thing and I create another list of instructions or another list of locations I could end up at if I was moving backwards from the end. And this is the key observation here, is this kind of meet in the middle approach, right? Can someone help me out by listing out all the locations I can get to using these 3 instructions? It might be a lot, I apologize, but it's helpful to illustrate this idea. I'll pause for a second because it might take a little bit. Thank you guys. Okay. Wonderful. Perfect. Okay. Oh, I love how it's sorted. This is so nice. Okay, wonderful. So we got, we're going to sort in order of x's first. We're going to sort by x and then by y. So we got -2, 0, or I should make these smaller. Goodness. -2, 0, 0, 0. No, thank you guys. I really appreciate this, honestly. Okay. 1, 0, 2, 0, 3, 0, 4, 0, and 7, 0. Did I miss any there? Or are we good? So I might be missing one. 5, 0. 5, 0. Oh, sorry, I just meant these first three. Apologies. Can we get to 5, 0 using the first three? I'm not sure. Oh, we can. Sorry. Yes. Yes, we can get to 5, 0. Yes, yes, yes. Erase them. Yeah, thank you. Math is hard, guys. I apologize. 7, 0. Okay, so these are our 8 options for the first bit. Now, can someone do the second bit for me? It might be a little bit easier now because we have a duplicate in the second bit. But can someone give me the list for the second bit as well? That'd be awesome. Or all of you. I love it when you guys are all sending stuff. It's awesome. Really cool. Perfect. Thank you guys. Wow, you guys are like in sync too. I don't know what's going on over there. Are you guys all in a room together, just like figuring this out? That's funny. Okay. We're gonna sort by X's again, and then by Y's. Ooh, this one's already got it sorted. Awesome. Love to see it. I think we're missing some negatives in there potentially, but that's okay. Let's see. We got 0, negative 10. Is there a? Is it 0, 0 next? Yes, 0, 0, 0, 10. Yeah, 0, 10, 0, 20. 5, yeah, 5, 0, 10, 5, 0. There's so many. I gotta space myself a little better. 0, 10, 0, 20, 5, 0, 5, negative 10, 5, 0, 5, 10, and 5, 20. Am I missing any, or is this all good? I feel like I might be missing 1 or 2. Can I get a thumbs up, or am I missing one? I really feel like I'm missing one here. Okay. All right. Well, regardless, we'll move on. Okay. Cool. Thank you guys. Okay. So now we have these 2 big lists, right? But they're computable lists is the idea, right? So since we've halved the operations we're considering for each side, now we have 2 lists that will give us some offset. And we want to know if we can combine any of these to get to the end, right? Now, the brute force approach unfortunately doesn't work here, right? We can't just try all combinations of each side because that'll give us 2 to the n over 2, which is the number of operations on one side, squared. And unfortunately, that just gives us 2 to the n again, which is not enough, right? So does anyone have any other ideas on how we can approach this maybe? I'll pause for a little bit because it's kind of hard to think about, but there is a way to do this. Binary search, interesting. Oh yeah. You can do this with binary. Actually, so I use a binary search solution as well. You can take 1 step past the binary search as well. Binary search in a second. Let's start with it too slow. Yes. Current instruction. This is desired instruction. Yeah. So Charlotte's nailed it. And you guys are a little bit ahead. But the main idea that I wanted to get at here, and you guys all got something good, was that we can kind of modify this second list here, right? Where we don't just want to consider the offset of each one, but we want to know that like the difference between these two, when we add them together, is going to be equal to some xg and yg, right? So we haven't really taken these into account yet. So if we want to search for a match for one of these guys, we actually know exactly where we want to end up at, right? So if we have 3, 0, then the instruction we want from the second list is what? it's xg minus 3 and yg minus 0, which turns out to be 210, right? So we're going to search for 210 in the second list to see if it exists. And if it does, that means we can use the combination of instructions we used to get this 30 combined with some value which uses it in the second list, right? So combined with some set of instructions in the second list, we'll end up with the correct ending location, if that makes sense. I think that was a bit of a convoluted explanation, but the idea is what Charlotte said, which is that if we have some value in the first list, we can combine it with a value in the second list equal to the final instruction minus the current instruction, or xg minus our x value, and then yg minus our y value. And this will give us some value in the second section that we need. Is that going to make sense? You guys following so far? Awesome. Yeah, okay, cool. And the way we do that is like Viraj and Kang were suggesting. There are a variety of approaches to this, right? One such way is to binary search, right? So I already presented these solutions as sorted, right? So that makes this kind of nice, where we can say, okay, I'm looking for 210. I can binary search in the second list to find 210, right? So I just binary search for the x's. I say it's going to be inserted somewhere here. And I'm like, oh, there's no 2 for the x's, so there's nothing here, and we don't add to our total. And we do this for all the values on the left side. So that'll end up being hopefully 2 to the n times log base 2 to the n, which is equal to n times 2 to the n. And this actually should technically pass. But for those of you that actually implemented this, you know that it ends up being a little bit slow. The reason is because you have this huge constant factor because you have these massive lists. And also because it might end up that when you're counting the number of values that match, it's possible that a really large portion actually do match your original location, right? So say all these items were equal to 310, then you have to iterate through all of them to add to your total, right? And if you do this for all the different values on the left side, we're going to end up squaring our value again, which is really bad. So I think duplicates do actually slow you down if you're not careful here. So another solution, like I think someone mentioned, and the solution used in the, actually no, we can do the hashing solution first. So you can do binary search here. You can also do hashing, right? So you can hash all the values on the right side and check with O of 1 time whether or not that value exists, right? Or store some sort of frequencies or something. But hashing is really hard here because the values are so big, like someone mentioned. So there's, we should write these out. This is very interesting. So binary search approach, hard to count duplicates. I think all these approaches are valid, by the way. You just have to be very careful with some of them. Log n factor makes it hard as well, right? Because you don't have a lot of playing wiggle room. Hashing, you get O of 1, right? So it's efficient enough, but hard to work with big numbers, right? So it's hard to hash the values on the right side, the locations on the right side, because you have values that can be up to like 10 to the 9, and you're working with negative numbers, and you have both x and j, or x and y, that could be up to 10 to the 9th, right? And then you also have this like number of instructions term that you have to figure out for, and so on and so forth, right? So it's a lot of work getting this hash function to actually work and being able to store it in a table that like handles collisions well and efficiently. So it's actually equally difficult, it turns out, to hash these values. And then the last approach is the sorting solution. And this is what I think was given as the official solution. And the idea here is instead of like binary searching for each element on the left side to the right side, we just take 2 sorted lists and kind of keep pointers as we iterate through them. So to illustrate that more carefully, Let me go back a little bit to where I had the lists before. This might take a second. I really should have just kept the list there. Cool. Nope. Yeah. So you could use a hash map. But if you're using a hash map, what are you hashing? You know, Charlotte, so you could have objects you're hashing, right? So maybe you store each of these locations in a location class, right? But then you need to implement the hash code method in order to hash these values, right? And when you're implementing the hash code method, you're going to run into this problem of, I have huge numbers here. What buckets do I put them into, right? Does that make sense? Or am I missing something that you're saying? Feel free to unmute too. I know it's everyone's got their camera off, but it'd be a little bit easier to talk maybe. Come on. That's the answer too. Oh, sorry. Doesn't have a microphone. Oh, sad. Charlie, do you have a microphone? No worries if not. We can also just move on.
Sorry.
Hi. Oh, thank you. Okay. What was the idea for hash maps?
I guess after you get the pairs like through, I don't know, bit calculations, I guess you use a hash map to keep track of the instances of each pair. And then use like combinatorics to kind of figure out the total number of instructions that you can use to kind of get to the end. I don't know if that was.
No, yeah, that's interesting. I was wondering, so you mentioned a hash map. Is the combinatorics being applied in the hash map? I'm just trying to understand.
Yeah, kind of like that.
Okay. Interesting. Combinatorics. I think you might be a few steps ahead of me. How would combinatorics be used in the hash map? That sounds really interesting. Okay, sorry. Very interesting ideas. But yeah, I think you actually can get really clever with your hash functions here, which is why I was asking Charlotte. So I bet you could solve it in that way. Yeah, it just gets difficult, I think. But yeah, that's a really cool idea. Yeah, the other way to do it is to do sorting on the left and right sides, and so we can kind of keep a pointer as we go down each side to compare these values. So first off, instead of storing these values themselves, we store these values subtracted from xg instead. So instead of storing 0, -10, we store 510 minus 0, -10. So we'll have 520. We have 510, 50, 5 -10, 5 6, no 0, 30, no 20, -20. No, that's just and so on and so forth, right? And so now we can directly compare these values to see if they match up, because if they do, then we're going to end up with our solution, and we can iterate down through these values to figure out where they match up with each other. So here we know these values aren't going to match up. We can kind of run all the way down to here where they start to, actually I should just write out all of these values so that we see them on here. So what is 510 minus this? 510 minus this. 510 minus this would be 0, 10. Wait, there's no way I'm doing this right. Oh. 0, 10. What am I missing here? 0, 10, 5, 0 minus. Oh, here we go. Okay. 0 minus 5. I guess it's because we end up, yeah, okay. So we go down the left side, we end up with like the 5, 0 matching it with this 5, 0 or something like that. Gotcha. Okay. Yes. Okay. Sorry. I'm confusing myself a little bit here. But the general idea is that if we iterate through these in the same order, right? So remember, we're doing X's and then Y's. We're going to first end up with the left side kind of catching up with the right side down here at 5, 0. So they're going to kind of match up at this point. And then from there, we can kind of walk through and see which values match up. So we know these values are the same, which means we can combine them to get the value we want. And indeed, we can combine 5, 0 with 0, 10 to get to our end goal, which is 5, 10. Right. And so we kind of walk down through both lists, being a little bit clever about how we add to our counter in an efficient way. Right. So if we might end up with the same issue as before, where if all the values on the left side are the same and all the values on the right side are the same and they all match up, then we're going to end up doing an n squared or a 2 to the n over 2 squared operation. So you have to be a little bit careful in how you move those pointers down. But the idea is if you go down the left side and go down the sorted right side, then you find values which match each other, you connect them, and you add to your total. Is that okay? It's very similar to the binary search solution and the hashing solution, but it's a little bit more, or has a little bit more observation and a little bit more care when iterating through. Is that okay? Are you guys, is this okay with you guys? Or is there some confusion still? Okay, I think I might have lost some people. Makes sense. Okay. All right. Okay. We got, makes sense. Iterate through the left side and right side. Cool, cool, cool. Thumbs up from Charlotte. Awesome. Thank you guys. Okay. Then in that case, are there any more questions on this problem? We can move on to the next one. I'm happy to clear up any confusion. I think this was gone through a little bit confusingly. That's my bad. So if you guys have any questions, I'm very happy to go. This is your optimal using pointers that really affects speed. Yeah, when I kind of confused. Okay, gotcha. Okay, optimizing pointers. I say pointers in the sense that we have a variable that knows what index it's at, not in the C++ pointer sense necessarily. Okay, so it's kind of confused. Okay, so in that case, we can go back through it real quick. So the main idea is that, Kang, your solution, did you use the binary search solution or did you use the hashing solution? Or none of the above? Binary search, okay. So in your case, you took all the values on the left side, right? You took an individual instance and then you binary searched across all the values on the right side. You said, okay, where is there a match here, right? Is that correct? Okay. Now, notice that these values, if you sort and binary search on everything the exact same way, these adjacent values on the left side are guaranteed to map to somewhat adjacent values on the right side. Or they're going to binary search to around the same values. Does that kind of make sense? Because they're in order, right? So this guy has to point to something above the second guy. Yes. Yeah, exactly, right? So instead of binary searching every single time, you know that if any one pointer binary searches the sum value over here on the right side. Let's just say these are two values here, and this guy binary searches this value on the right side. Yeah, then you know that if you were to binary search, this guy would have to binary search to somewhere in this range up here, right? So instead of just binary searching every single time, what you can do is kind of iterate through the left side downwards and iterate to the right side downwards and keep track of where it's matching up, right? So in this case, maybe you know your last pointer by binary searching from the left side was right here. And you know that in order to figure out the next guy's location, instead of just binary searching again, we can kind of just walk down to the next guy here in this list. And the reason this makes it faster is because we're only going to be walking down. We're never going to walk back up, right? So the total time it's going to take us to reach the end is linear in both sides. Is that okay? Yeah, so it does mean every single possibility is only considered once, right? So in the case where you have multiple that might match, it complicates things a little bit, but this is the general solution where you're trying to pair values from the left and the right sides, right? That map to xg. And the way these are paired, which I might not have touched on, it also is a little bit special, where not only do we have to store all the subset locations, but we have to keep track of, like Charlotte mentioned, how many instructions each of those subsets used, and kind of add them to the number of subsets used in the right subset to figure out how many total subsets were used as well, which makes this even a little bit more complicated potentially, right? Because we're not always going to be using some from the left subset and some from the right subset. We need to keep track of the total number of instructions used across both, and using those values when we match to instruction subsets, we will end up with the number of bits used in each of these cases. So in this case, we're going to pair, say, oh goodness, we're going to pair like -2, 0, 3, 0, and 4, 0 from the left side. That's going to give us 5, 0. And we're going to pair that with 0, 10 on the right side. So the total number of instructions is 3 plus 1. And we just keep this number of instructions used with each of the subsets. And so when we combine these two subsets together in the matching thing we saw earlier, say these are the subsets, we just add this subset or this count to the fourth value, right? Because you know that we use 4 bits, 0, 1, 2, 3, or is this 4? It's 4. So we increment this one by 1, right? So we say we found a solution that uses 4 instructions, so we're going to increment the number of solutions for 4 instructions by 1. And we can do this for all of the pairings. Does that kind of make sense? Are we all okay so far? Okay, cool. Wonderful. In that case, we'll go on to the third problem real quick. Email filing. This one's interesting. Okay. So we have here, just to refresh your guys' memories, we have some number of emails, or sorry, some number of folders on the left side. And then we have some emails, make them boxes on the right side. But we can only consider some window of these folders and emails at once. So if our screen is like here, then we're only looking at the first folder and the first 2 emails. And we can only move our window, our sliding window, down 1 step at a time. We can't move it back up again, right? Now, we can move the window up technically, because if we remove emails and we're in the bottom window, so say, for example, we removed this email, then this email would kind of move down to replace it. In that sense, we can see previous emails, but besides that, we're never going to be able to see anything that we scroll past, right? Now, the key observation here is that we can't ever go back on the left side, right? We can't ever go back and add more emails to a folder, right? Or actually, sorry, I think one thing I left out is that you scroll on both sides. Yeah. Yeah, so there are two windows, my apologies. You have a window on the left side and a window on the right side. So say we might be here, seeing 2 emails on the left side or something like that, or I guess it would be 2 and 2. So say this is your window. When you scroll down here, the view becomes the next 2 emails and so on and so forth. But when we scroll down on the right side, again, we can see previous emails if we're at the very end. And we delete the top email because this one will come down to replace it. This cannot be done on the right side. So if we can't delete a folder and move anything down, whenever we move down past a folder, that folder is kind of lost. And because of that, the only viable solutions have to assign all the emails on the right side to the first folder before we scroll past the first folder. Does that make sense to everyone? So before scrolling down on the left side, we have to make sure. Okay, cool. Wonderful. Yeah, we just got to make sure that before we move past folder 1, I'm going to label them real quick. This is 1, this is 2, this is 3. Got to make sure we assign all the emails that need to go in folder 1 to folder 1 before scrolling past it. Right. So say this was 1, 3, this is 2, this is 1, this is 3. Say this bottom email needed to be assigned to the first folder, and our K was 2. Then we'd have to scroll all the way down till we get to that folder to assign it before moving down to the second and third folders. And it turns out if we're really careful, since we now have a greedy algorithm for doing this, right? All we have to do is just assign all the emails on the right to the first folder before moving down to the second folder. And we repeat that process for the second folder, where we only scroll past the second folder when all the emails that need to go in the second folder are in the second folder. And we continue doing that for all the folders, right? So for the first folder, we do the same thing. For the second folder, we do the same thing. We scroll down. We keep doing this until we get to the bottom, and we see if it works, right? And we can simulate this process in n squared time by just kind of trying it out, right? So we start off at the very top for k equals 2. We say, okay, we're going to first assign this guy to this folder. This guy goes away. Now we have a slightly larger window because we're always encapsulating 2, right? And then we say, okay, the second guy can go in the second folder. We just let that happen. And then we lets us go down one farther. And it turns out this actually lets us do this without scrolling. So we can actually put all the emails here into the first and second folders. And then we're just left with 2 emails left. So we scroll down by 1 and continue from there. So let's work this out for the sample case. So it might be a little bit more interesting. Or we'll do it for the second to last case, I think. Is this a yes? It was a yes. Yeah, so that'll be interesting. Okay. So let's say our folders are 1, 2, 3. I'm unsatisfied with my drawings today. I'm sorry. I was telling the bronze group earlier that I'm absolutely not an artist in any sense, but I'm trying my best over here. So it's going to cut me some slack. So that's 2, 3, and these are our folders. And then on the right side, we have our emails, right? 1, 2, nope, already messed up. 3, 2, 1, 3, 2, 1, 3, 2, and 1. Is that right? 1, 3, 2, 1, 3, 2, 1, 3, 2, 1. Okay, lots of 1, 3s and 2s. So we start off with our windows like this, and we got to get all the emails that are in the first folder, right? So we start off and say, okay, this guy can go in the first folder easy. We move down 1. Or sorry, all the guys move up 1. So now our window is here. We move the second guy to the second folder. Scroll down 1 again. Move this guy over as well. And so on and so forth, right? So we're going to end up eliminating that guy. Now we have 2 3s, right? This is where it gets interesting. Here's where we get to a spot where we actually can't scroll down without losing this 3, right? But unfortunately, we have to get all the 1s into the 1 folder before we can do anything else. So we actually skip over this first 3 and move on to the second bit, right? So this 3 up here is kind of lost, but it turns out that's okay. So we now remove the 2. We remove the 1 as well. And now we end up with 2 3s again. So we have these 2 3s here. And now we have to miss this 3 again, unfortunately, on top. End up with 3 2. You can cross out the 2. You can cross out the 1. And now it turns out we have these 2 3s back again, right? So now this 3 has been shifted down, and we've put all the 1s away, fortunately. So now finally we can move down to the second 2 folders and remove the last 2 3s. Is that going to make sense? Is everyone okay with that? Okay, cool. Awesome. But yeah, basically the idea is we just simulate the process, right? Which sounds very simple, but we do have to be very careful in how we do it so that it is efficient, right? So when we want to know how far down we have to go, and when we're removing these values and adding these values and stuff, it's not so easy, right? So maybe we don't have a queue. If you use a linked list, that's a very good idea for the values we're adding and removing as we go down, right? And then we also have to know how far we have to go down for each folder, right? So for that, I think the Java solution used a priority queue or something like that, just to know where everything is and how it has to be removed and so on and so forth, right? So you have to be a little bit careful in how we simulate this process. Let me erase some of these guys. Cool. So for example, at the beginning, we might know that the 1 has to get down to, this guy down here. The 2 has to get down to this guy down here. And the 3 has to get down to this guy. And so we just iterate all the way down, kind of forgetting values as we go, right? But it's okay to forget these values because at the very end, we just check if we can go back up and remove it, even if we forget some on the way down, right? And so we just kind of try our best going through this process. And sometimes it'll end up that it doesn't work, but that's just where we output no. Is this okay for everyone? Pretty okay? I think it's very high level, but this is the general idea. It's just we want to do a slightly complex simulation. Pretty okay. Okay. So best. Okay. Do you guys have any specific questions on this? Yeah. So that's a general idea, right? Is for each folder, you figure out how low they have to go. And I think this can be done efficiently. So in this case, we have, what is it? We have n folders. And for each folder, we just figure out the lowest value they have to go. We can do that using a priority queue. I think there's a simpler way to do it too. Just figure out the lowest one. And then we just go down for each folder until we reach that lowest one before switching on to the next folder. So we pre-compute the lowest email that each folder needs to reach. And we just kind of slide the window down there, removing emails as we go, using a linked list or whatever other method we have. I think a linked list works here because, although maybe not. I think you might have to use a set or something along those lines, something that can hold sliding windows and add and remove efficiently, right? So you might need like a multi-set for C++. For Java, you might need like a frequency map or something along those lines. Anything that keeps track of the emails on the right side and can add and remove to that efficiently, right? So say, for example, we had a multi-set on the right side, and we were looking at emails or folders 4 and 5 on the right side. Say we had like, we had 4, 5, 6, and we had 7, 5, 2. I'm drawing on, scroll up here. Yeah, so say we had 4, 5, 6 in our window on the left side. And the emails we were looking at were, we'll say 25, 11, and 7, but we were only looking at this window right now. We might want some kind of a frequency or multi-set on the right side, storing like, okay, there's 120, there's 15, and there's 111. And so as we add new folders, we might want for each of these folders to say, okay, is there an email on the right side that is equal to this email? And if so, we remove it and we add the next element to our multi-set, right? So now we had a 7 here instead. And if we have a multi-set that's efficient, or I think like a hash map or a tree map in Java will work just the same way, then we can do these operations efficiently enough such that we can walk down the entire tree, right? Walk down the entire set of emails. And at the very bottom, try to remove as many emails as we can such that we don't miss any of the ones that we forgot before, quote unquote. So we're going to end up going all the way down, and then we're going to have some list of emails that we might have forgot. So before it was like 3 3s that we kind of skipped over, and we check if we can remove these just by removing the emails in here that we forgot as well. Does that kind of make sense? Maybe I can illustrate it again, but with the multi-set this time, and that'll help. Or if you guys have a specific input that you want me to do, or we can map one out together, that might help a little bit. But essentially, the reason it's hard to talk about is because it's just a simulation, and there's just some details that need to be added in, right? So there are a lot of ways to keep track of the emails on the right side. I think multi-set is one way to do it, but yeah. Any thoughts on this problem or any of the other problems that you want me to go back to, or questions on that? Yes, Raj, you can ask a general C++ problem. Review the first problem. Yeah, Raj, what's a question? Nico, I see your question. I'll answer it after Raj asks his C++ question. Very good question. So standard vector is a generally somewhat slow in a lot of competitive programmers' minds. So if instead you can bound the size of your list, that makes things a lot more efficient, right? So say instead of using a vector, I can just keep track of, and the reason for that is because every time you add an element to a vector in C++, it also has to allocate memory for that new thing and potentially like shift your array somewhere else. So you imagine, and I'm not sure if this is entirely accurate, but this is the general idea. It's not exactly how it works, but the general idea is when you have a vector in C++, it takes up some amount of memory. So say you have like garbage over here and garbage over here, and this is your vector. Whenever you add new elements to that vector, it has to like add it to your memory somewhere too, right? And if you end up adding elements somewhere where there already exists memory, suddenly you got to move that vector somewhere else in order to make space for it, right? And this is a general problem with any kind of dynamic object in C++ or Java or any programming language. But generally, if you have something that changes in size, your system has to reallocate memory for it depending on how big it is, right? Because you're not telling it how big it is. So if you end up in this scenario where you go past the amount of memory that was expected to be used by that object, so say like you add one too many elements and it kind of goes out here, outside of the tank of memory it was allocated, then you got to find a whole new location for it inside of your system memory, right? So this is why dynamic systems are slow. What was that? Yeah, that's a very good point. The answer is technically no. There would be no difference in performance to an array, I don't think. But also, primitive objects are faster in general than vectors. But if you were to just allocate a certain size to the vector, yeah, that too. Yeah, that's a good point, Kane. So generally, you do want to use primitive types, especially if you can bound the size of your array. Because if you're using a dynamic type like a vector, first of all, there's some kind of overhead just associated with using a larger class or object, or a slightly more advanced one. And your compiler has to deal with like reallocating memory for it, or your runtime environment has to deal with that. Cool. Does that make sense? So if you can bound the memory, and also like if you can bound the size of your vector, you might as well just make it an array, right? Because you're not going to need to change the size of the array at all. Anyway, std array and built-in array. I'm not familiar with, honestly, I program in Java, so I'm not 100% familiar with all the different types. What is std array? I'm super rusty in C++, so I imagine it's like some wrapper for the actual array class. It has out of bounds. Oh, okay. Oh, yeah. Okay. Gotcha. I imagine they're very similar to one another. I see. Yeah, that sounds much nicer. I remember programming C++ in some of my classes, and it was so frustrating because when you go out of bounds, it doesn't tell you. It just gives you some garbage values at the index instead, and it's quite frustrating. Yeah, it's a lot of undefined behavior. I think generally you want to use primitive types if you can, but sometimes the debugging of like, or the error messages you get using these other types is quite helpful when you're debugging, right? So for example, you do want to be getting out of bounds exceptions if you're going out of bounds, because that's helpful for knowing what's going on. Yeah, I learned something new today. Thank you guys. Nick, I think you had a question about problem 1, or Nico? Do you mind unmuting, or do you want to just message about it? I can go over it again, but I was wondering what your specific implementation was. I think there was some speed questions for question 1, potentially. Oh, okay. He's got it. Awesome. Cool. Do you guys have any other questions about this competition or just competitions in general? General advice or other interesting questions you guys have? You guys have been awesome today. Thank you. Anyone else? All right. Well, thank you guys so much for coming. That was faster than I thought it would be, but really good job today. You guys are awesome. This is a really hard silver contest, so congrats to you guys for even attempting it. It's really good stuff. And if you have any more questions, feel free to email me. My email is, and I'll be sure to get back to you with any more questions. I can probably be a little bit more in depth if we're offline than I can here. But also, if you have any general questions, feel free to let me know right now, and I'm happy to help out. So, other than that, have a nice rest of your Sunday, guys.